So in this session, we shall we shall conduct analysis of continuous beam using STAAD Pro software. In this session, we will look into some of the common errors we encounter while preparing the model, and we shall look into the different loading patterns. In previous case, we have used only concentrated load and UDL. In this case, we shall go for different loading patterns, that is uniformly varying load, concentrated movement, and apart from that, if the UDL is given for a particular portion of the beam, that is not for the full portion of the beam. So in this case, he has given UDL only for initial 2 meters from the left support. So how to assign these different kind of loads and what are the common errors that are encountered, we shall look into this in a video. So now your STAAD Pro is already open. So what are the spans? The 4-meter span, 5-meter span and 7-meter span loaded with 20 kN per meter of UDL, which is only for 2 meter, 50 kN of concentrated load at a distance of 2 meter from the left support, and a concentrated moment of 40 kN meter at a distance of 3 meter from the left support, and an uniformly varying load of 20 kN at for this 7-meter span of the beam, and I and section property of the beam is given as I, 2I and 1.5I, where I is equal to 1010 into 10 raised to 6 mm raised to 4. This is the input data given. So let us prepare the beam. The initial point should be at 0, 0, then 4 meter, 5 meter, 7 meters. So Control C, Control V in X direction, 4 meter, Control C, Control V, X direction, 5 meter, Control C, Control V, X direction, 7 meters. Now, either we can go to geometry, add beam from point to point, or here is its shortcut. So, I am adding here. So, these are the different views. This is I have selected front view. If you select this one, you can see it in 3D. If you select this one in top view, if you select this one, this is the side view of your beam. So you can only see the point here. So this is your, I will keep it in front view. Now we have to assign support, general, support, create. All the supports are pinned supports. So add a pinned support, select this one, select all the nodes, assign to selected support. Now go to general. Now we shall assign loads and definition. In this case, what I will do is I will define what is the self-weight of the beam and apply loads as the live load on the beam member. So add here. So first load case is a dead load, that is a self-weight of the beam. Let us add this one. Now live load on the beam, that is imposed load on the beam. So imposed loads on beam. So I will add this one, close. So in this self weight of a beam, add. So go here, this is given as a self weight and is indicating it as -1. What it will do? It will do calculate the self weight of your beam. So let us see how it will calculate the self weight of the beam. While assigning the properties, we will be, so see here, while assigning property, define. So see here, this is a concrete. So concrete, it will recalculate its density and multiplied by volume, we will get the self weight of the beam. So that's why he has given it as in loads and definition. If I try to add self weight, if I go to add, so he has given a factor -1. So let us see here how the software will calculate. Let us think that So now let us think that your beam is of 30 by 450. So what it will do? 0.23 by 0.45 into 25, that is density of your concrete, will give the answer in terms of kilonewton per meter. In this manner, it will calculate the self weight of the beam in terms of kilonewton per meter, and it apply to all along the length of the beam as an dead load, that is self weight. So this is an pre-built matter, so we can add close. So I have to take self weight of all the names. So what I will do, I will assign it as assigned to view. It has got assigned to view. So every member got assigned. So if you click here, you can see here all the members are shown in red marking. So it indicates this load has already got assigned. Now impose loads, add. So what are the loads? Member loads. So what is the load? 20 kilonewton per meter from 2 for 2 meters. So minus 20 from 0. So here he is indicating D1, D2. D3 is a perpendicular distance. D1 is nothing but from left support where your load should start, and D2 is at what distance your load should end. So my load is starting here from left support, it is starting at 0 and it is ending at 2 meter. What I will do here? 0 to minus 20 kilonewton per meter. Add. And now concentrated force of 50 kilonewton at a distance 2 meter from the left support. Minus 50 at a distance. Okay, here he has shown D1. He is measuring D1 from the software is measuring D1 from the left support. So D1 distance is 2 meters. At a distance 2 meter. Add. Now concentrated movement of 40 kilonewton meter at a distance of 3 meter from left support. So here concentrated movement. Select on concentrated movement. What is the value of concentrated movement? 40 kilonewton minus 40. It should, where it should act, it is acting along your perpendicular axis, that is if this axis is z axis. See here, this is your z, so it is acting along z axis in clockwise direction. So let us assign 40. It is acting in local about local z axis in clockwise direction. Add. Close. Now select this one. Add. We are left with the uniform varying load, member load, linearly varying load. Select. At this distance, at the initial point it is 0, at end it is becoming 20. Add. Close. Now select this load. This is a GY20, uniformly distributed load. This is started at 0 and ends at 2 meter. So use cursor to assign. Select. So I have assigned the load. It is acting in a downward direction. Let us see what happens if I add. If this minus sign is not added, I will change here. Change. Close. Your load is acting in upward direction. That's why we are giving it as a minus 20. Change. Close. Your load got changed. Now concentrated load of 50 kilonewton in second span, and movement is also in this span only. Assigned. only varying load. Since it is given positive, it is acting upward, minus, change, close, so now it is acting in downward direction. So see here, your movement is showing here in anti-clockwise direction. To make it clockwise, what I have to add is minus 40, change. So now you can see the load is acting in clockwise direction. The scale of this load is very high. So how to change the scale? Come here, select the scale, select over this scale. In this point moment, that is concentrated moment, let me increase this value to 20, somewhere around 50. Apply. Okay, now you can see it as showing. So the value will remain same, only the size of that diagram will reduce here if we change the scale. So I will make it 75. Apply. Okay, so you can see here at that point it is shrinking. The size of the drawing is getting shrinked. If I make it 100, here you can see it is acting at some distance from this member. Okay, we have assigned beam member, we have assigned supports, we have assigned loads. Now we have to assign the properties here. So how to assign the properties? In this problem he has given I, 2i and 1.5i. The value for I is equal to 1010 into 10 raised to 6. Let us calculate the dimension of the beams. For rectangle, let us assume breadth of the beam is equal to 230 mm. I is equal to BD cube by 12 for your rectangle. So your D is nothing but cube root of 12I divided by breadth of the beam. In first beam, I is equal to 1010 into 10 raised to 6. D will be equal to cube root of 1010 into 10 raised to 6 into 12 divided by breadth of the beam 230. So depth of the beam will be equal to depth of the beam will be equal to 374.9, approximately equal to 375 mm. So your first beam dimension is 230 cross 375 mm. Next beam is of 2i. So that is nothing but 2 times of 1010 into 10 raised to 6. That is nothing but 2020 into 10 raised to 6. 2i is equal to. Now what will be your depth? Depth is equal to cube root of 2020 into 10 raised to 6 into 12 divided by 230. This is equal to 472 mm. So approximately I will round it off to 475 mm. So next beam dimension is 230 by 475 mm. One more value is 1.5 times of I. 1.5 into 1010 into 10 raised to 6. This is equal to, if I calculate, D is equal to cube root of 1.5 into 1010 into 10 raised to 6 into 12 divided by 230. You will get beam depth is equal to 429.16, approximately equal to 430. So this beam is equal to 230 by 430 mm. So this is for I, this is for 2I, this is for 1.5 times of I. Okay, so now we have to assign these beam properties in your model. Go to general property, define rectangle, depth width of the beam is 0.23 fixed, one is 0.45 add, another is 0.375 add, another is 0.43 add. So I is nothing but 230 by 375. Select 230 by 375. Select this beam, assign to selected beam, click on this what assigned R2 property assigned to this member. Next one is 2 times of I. 2 times of I is nothing but 230 by 3, sorry 475. 230 by, we have defined here 450. Let us change it to 475. Change. Next is 230 by. The member properties are assigned here. Now save this one. Go to general, loads and definition. In this case, we have assigned one is self-weight, another one is imposed load, that is live load, one is dead load. So what I will do here, go to load combination, add. I will define auto load combination as per Indian code, generate 1.5 times of dead load, 1.5 times of, I will unselect this one, discard the load combination, select this load combination. So for a combination, for load 1 I am multiplying it by 1.5, for load 2 I am multiplying by 1.5. So selected load combination is 1.5 times of dead load and 1.5 times of live load. Add this one, close. So from this you can know what is the factored bending moment, factored shear force, what is the deflection for given loadings. Now, what are the preliminary errors that we may encounter in this model? So, the next step is to give analysis, add, perform analysis. So, I am not adding this one. If I analyze directly, what happens here? It gives an error warning. So, see here, it is showing two errors. View the output file. Done. So, what is showing error? Error is a finish command in load data. Error above line contains erroneous data. These are the two errors it is showing when you are not given perform analysis. So what I will do, I will close this one, go to perform analysis, add, close. Now analyze the beam. So see here, your beam got analyzed, no errors, no warnings, nothing. Done. So apart from that, one more common error is encountered is we forgot to assign the beam properties here. If we not assign the beam property, what happens here? Let us see. R3. What I will do? R3. I will delete this one for time being. So this beam has not assigned with any member property. So if you analyze this one, run analysis, save. So it will give some error. So it has got two errors, that is elastic property is not assigned will be the error message. Then see here, elastic modulus not entered for the member. This indicates, and section properties not entered for the member. This indicates that one sum of the member is missing. Your sum of the member hasn't assigned with the beam member property. So select this one. Right now I will assign the whatever the property is there. Analyze and see this one. So this is how you can analyze the things. Errors and warnings are removed. Done. Now go to post processing. Here you can see bending moment, shear force. I need bending moment and shear force for factor load, as usually we conduct designs for limit state of design. Limit state of the collapse, we go for factor loading. We will not be considering here in that is directly the service loads. So on this generated Indian code is having 1.5 times of dead load 1.5. So I am selecting only this load, apply, okay. Beams, forces. Now whatever you are getting, bending moment, shear force will be of a factored load. So go to results, view values, beam, maximum bending moment, annotate, close. Now you can see here 94.429 is a negative moment here and 31.154 is the moment here. If at mid bending, if you want, go to results, view values, beam results, midpoint and ends, annotate, close. At midpoint 63.311, 57.762, 20, 31, 94. 94 is negative bending moment, 63 is a positive bending moment.